Okay, good morning. So here in this video I am going to explain downsampling and upsampling with the examples. So downsampling means here the system is downsampler, so which reduces the sampling rate of the x of n. That means here x of n is the input, output is y of n, that is equal to x of n into capital M. Here y of n is nothing but x of nm. So here consider example m is equal to 2. So take the m is equal to 2 here. So now in that case I am giving one x of n here like this. So 0 to 8. So here amplitudes are like this. Now what is the output? Yd of n. So that means here just given like m is equal to 2. So otherwise we may use the letter capital D. So capital D is equal to 2. Capital D is equal to 2. That means x of n is decimated by a factor 2. So now here see this. So x of n is decimated by a factor 2 means which is denoted as x of 2n. That x of 2n is equal to. So here from the x of n, how can you find out the x of 2n? See this. So here 2n means here also take the samples 0, 1, 2 and so on. Here substitute 0 in this, x of 2 into 0, x of 0. So see the value in the actual signal x of n. X of n is equal to at 0, 0. That means, so here also you can get the 0. Now substitute 1 here, x of 2. X of 2 means here what is the value? 2. So take the amplitude. So 2 means x of 4. X of 4 at x of 4 value is 4. So now at 2 place that amplitude value. So now here in the similar way complete all the values. Then here x of 8 up to x of 8 we have the values. So here so remaining values are 0. That's why here if you substitute 4 you can get the x of 8. Then you can get the value here 0 and remaining values are 0. That means this is the x of n. And then x of 2n is nothing but this one. That means here this one is having the one sampling rate and this one is having the another sampling rate. Okay, right? So now this x of n is decimated by a factor 2 or downsampling the here downsampling has to be done here. So that's why you can get the output like this for the decimator. So in the same way here decimation by a factor d, right? So we will discuss here. So assume here x of n with the spectrum x of omega. So we have to downsample this x of n by a integer factor t. So now here observe the x of omega, that is a spectrum. So it is the non-zero value, non-zero in the frequency interval 0 to pi. So here our mod f less than or equal to fx by 2. So you may consider anything. So that means here x of omega is having certain values in this period only. Other than this one is the 0. That means this is the band limited signal. It's okay. If you reduce the sampling rate simply by selecting every dth value of x of n, the resulting signal will be an aliased version of x of n with a folding frequency of fx by 2d. That means, so here if you just reduce the particular sampling rate, so in our desired with our desired value, so maybe you can get the aliasing version of the x of n. That means so here which loses certain information. So that's why here to avoid that particular aliasing, so should consider the what is that here this particular d value. So right, so here that means to reduce the bandwidth of x of n to f max, that is equal to fx by 2d, or omega max, that is equal to pi by d, then downsample by d and thus avoid aliasing. That means here so based on the spectrum value, right, then so consider the here bandwidth limitation, that is f max is equal to fx by 2d, right? If you follow this particular condition here, so from this omega max also pi by d. If you follow this one, so then here we can avoid the aliasing in the downsampling action. So here of course you know that without aliasing, what is the sampling rate means Fs should be less than or equal to 2fm. So here we should maintain Fs equal to 2fm. So where Fs is the sampling frequency, Fm is the original signal frequency. Based on this particular technique here, so we just here take the condition Fmax is equal to Fx by 2d. Okay, right. Now, so here illustration of decimation process. The input x of n is passed through a low pass filter, so which is having the impulse response h of n. Then its frequency response also given here like this. It is equal to 1 for mod omega less than or equal to pi by d. Thus, the filter eliminates a spectrum of x of omega in the range. What is that? Out of the range. So here this filter eliminates the x of omega values, right? Then here you can get the what is the decimated version of the x of n. That means here use the one filter, right? Use the one filter. So based on this, we just control the frequency response, frequency spectrum, right? Frequency spectrum. Then you just downsampling the particular signal. Okay, right. This is the technique here. That's why here x of n is given. Use a filter, then output, then downsampling, then you can get the output, right? So now here sampling rate is 1 by tx here, fx. Now what is the fi here? Fx by d here. Okay, right. So here some mathematical illustration is there. So find the output of the filter here. So use the convolution formula. And then output is nothing but here y of m is nothing but in terms of v of n, v of md. Of course, if you do the decimation, so just write like v of nd as I said in the decimation definition. Now y of m is equal to v of md. So here substitute here x of n minus k is nothing but, so then y of m is equal to v of md. So now here summation h of k, in the place of n take the md minus k. So x of n is here LTI system. So now, so then by considering this here, frequency domain characteristics of the output sequence can be obtained by relating the spectrum of y of m to the spectrum of the input sequence x of n, right? So now here, so if you define v dash of n like this, so n is equal to 0 plus or minus 3 plus or minus 2d only we have the value, otherwise it is 0. Then you can get the here what is that, a discrete Fourier series representation of p of n like this. So since v cap of n is equal to v of n into p of n, to get the output y of m here, y of m is nothing but v cap of md. So here based on this here, just apply the z transform of the input sequence y of m. So now here y of z, you can get the y of z. So here substitute the y of z is equal to y of n into z power minus m, then substitute y of n here and then simplify, then you can get the here output like this. If you observe here, omega y is equal to 2 pi f by fi form, so it is, which is equal to omega y is equal to d into omega x. Okay, so here in this way you can downsampling the particular thing, and then we can illustrate this one with respect to this what is that graphical form also. So here v of n is taken like this, and then observe the p of n and v cap of n and y of n. So in this way you can downsampling the what is that input signal. So and this is nothing but the spectrum for each signal. So here observe the x of omega and then take the filter and then cut it off, and then you can get the output like this by multiplying these two, and then from this you just decimate, by decimating then you can get the output like this. Okay, right? In this way you can get the what is the decimation process. Okay, so here, so what is the decimation, and then example, graphical illustration, and then mathematical illustration. Okay, thank you.